Welcome! In today's lecture we're going to be exploring aromatic substitution reactions from Chapter 18. So in Chapter 17 we talked about how aromatic pi bonds are less reactive than typical alkenes. For example, the addition reaction of bromine to an alkene can occur quite readily, but when the pi bond is part of an aromatic ring, this reaction no longer occurs. In this chapter, we're going to look at some substitution reactions of aromatic rings and figure out exactly how we can get this reaction to proceed. The pi bonds of the aromatic ring act as nucleophiles, and the bromine acts as an electrophile. And so we saw with the previous reaction, either the nucleophile isn't strong enough because it's stabilized in that benzene ring, and that's coupled with the fact that the electrophile isn't electrophilic enough. So in order for us to get this reaction to proceed, we're going to need to enhance the electrophilicity of the electrophile. And we're going to do this using a catalyst, using an activation, not necessarily a catalyst, but a mode of activation such as iron. So when we subject benzene and to bromine in the presence of iron, this reaction will indeed proceed. And so there's a class of reactions that we can perform on the benzene ring. These reactions are called electrophilic aromatic substitution. In this case, the benzene ring is acting as the nucleophile, the pi bond of the benzene ring. Those electrons are the nucleophile, and we're going to expose them to some electrophilic species. And so here are a variety of products that we will be able to make by the end of this chapter directly from a benzene ring. So in a bromination reaction, for example, a bromination of an alkene, the alkene double bond acts as a nucleophile, and one of the bromines acts as an electrophile. In order for this type of reaction to work in a benzene ring, we need to enhance the electrophilicity of the electrophile. And to do this, we can use a Lewis acid catalyst. This will make the bromine more electrophilic. And so we can look at the structure. If we subject bromine to iron tribromide, bromine will nucleophilic attack the iron, and that creates this species as an intermediate, which essentially is a source of bromine plus, which is a more potent electrophile. So our double bond in a benzene ring will react with this species, whereas before it would not react with just Br2. And we can look at the mechanism of that reaction. The first step of the mechanism is that the aromatic ring, you guessed it, acts as a nucleophile and attacks the bromine, and this forms a sigma complex. The sigma complex consists of one less pi bond, right? We've broken the pi bond, one new carbon bromine sigma bond, and one carbocation. This sigma complex has lost aromaticity. We no longer have an aromatic ring here. The next step of the reaction is a proton transfer from the sigma complex. The proton that's directly attached to the bromine is deprotonated by the iron bromide complex, and these electrons, this is mostly like an E1 type mechanism, right? These electrons between the proton and the carbon then reform aromaticity in the form of a pi bond. So in the step 1, aromatic ring attacks the electrophile, and we form the sigma complex. Step 2, deprotonation of the sigma complex, which leads to re-aromatization. Now, there's two potential products of this reaction. Originally, we looked at an addition product, but if we look at the stability, the free energy, the thermodynamic stability of these two products, the substitution product is much more stable. And this is because we have an aromatic ring. If we follow the kinetic product, right, the addition product would be formed, but the substitution product is thermodynamically much, much more favored. So we will only observe the substitution product for this reaction. Not just iron will work for this reaction, but also we have the opportunity to use aluminum tribromide. So we have two potential catalysts, aluminum tribromide and iron tribromide. Both of these catalysts will work for this reaction. Benzene can also undergo chlorination, and this would use Cl2 and aluminum trichloride, or iron trichloride. So we can chlorinate and we can brominate, both have the same mechanism. Iodine and fluorine will not work. Chlorination will be too reactive, so too violent to be practical, and iodination will be too slow. So we have two extremes as far as fluorine and iodine, and this makes sense if you think about where they are on the periodic table and compare the atom size and electronegativity of these. But chlorine and bromine are the sweet spot for this to occur. We can take a look at the chlorination. Same mechanism. Step 1, nucleophilic attack. I mean, this figure is more or less just a copy pasta of the bromination figure, but with chlorine instead of bromine. Second step, proton transfer. In fact, all electrophilic aromatic substitution reactions will follow this general mechanism. So this chapter is easy. We just learn one mechanism, and it should get us all the way through. First step, nucleophilic attack, form the sigma complex. Sigma complex is resonance stabilized. The carbocation can move all the way around the benzene ring, and then we finish the mechanism off with a proton transfer that leads to re-aromaticity. The next reaction that we're going to look at is sulfonation. In this case, our electrophile is going to be SO3, and we'll use a sulfuric acid catalyst. So fuming sulfuric acid actually contains SO3 as a gas. We can look at the electropotential map for this and see that there's quite positive on the sulfur, which makes it a great electrophile. SO3 is a potent electrophile, and this is because of the significant partial positive charge on the sulfur due to inefficient pi bond overlap with the oxygen atoms. And as a result of this, the sulfur-oxygen bond has significant single bond characteristics. And this also means that it's going to be an exceptional electrophile for our electrophilic aromatic substitution reaction. So let's take a look at the mechanism. The first step is going to be our nucleophilic attack. This is the same as the general mechanism. We obtain the Zwitter ionic sigma complex intermediate, which can then be deprotonated and aromaticity reformed. This reaction has one additional step where the oxygen is protonated to yield the final product. Overall, this reaction is going to be dependent on the concentration of the sulfuric acid. The SO3H is a good leaving group, so in dilute sulfuric acid, mostly water, the reverse process is also possible. And we can look at the reverse process a little bit later in the chapter, but for now, we'll focus on the electrophilic aromatic substitution portion of this reaction. Nitration is another electrophilic aromatic substitution reaction. In this case, we use HNO3, and that will be the source of the electrophile, and we use a sulfuric acid catalyst as well. these two molecules are going to react together first to form the active electrophile. So for this mechanism, you will need to know how to form the nitronium ion before the electrophilic aromatic substitution actually occurs. So let's take a look at that mechanism. First, sulfuric acid will protonate the oxygen. This has formed a good leaving group, and then so this oxygen can push electrons towards the water leaving group, and the nitronium ion is formed. This is our active electrophile. We have an electronegativity difference between the two oxygens and the nitrogen, which makes the nitrogen extremely electron deficient. So looking at the full mechanism for this reaction, once we've formed our nitronium ion, nucleophilic attack occurs, sigma complex intermediate is formed, which is then deprotonated, resulting in reformation of aromaticity. We can then also use reduction conditions to form amine. So as you're kind of thinking about the spider web of reactions from this chapter, right? So far we've been able to form bromine substituted benzene ring, chlorine substituted benzene ring, sulfate substituted, nitro substituted, and now we can reduce our nitro down to the amine. This would be using iron or zinc, an acid, followed by base. So we can go from a benzene ring directly to amine using this sequence. The next reaction we're going to look at is a reaction that forms a new carbon-carbon bond. So up until this point, we've looked at a few ways to form carbon-carbon bonds. The Grignard reagent being one of the most prominent. This is a new reaction, a file under that category that you have of carbon-carbon bond reactions. This is called the Friedel-Crafts Alkylation reaction. We're going to take an alkyl halide, and in the presence of a Lewis acid catalyst, aluminum trichloride, we're able to form a new carbon-carbon bond. So the first step of the reaction is going to be to form our active electrophile. The chlorine of the alkyl chloride attacks the aluminum, and this can be thought of as a carbocation. Now, this is likely stabilized by close proximity to the aluminum chloride complex, especially if we're dealing with a primary alkyl halide. But in general, we can think of this reagent as a carbocation, electrophilic carbon. So our first step is going to be nucleophilic attack of that carbocation, which forms a sigma complex, which then can be deprotonated and reform aromaticity, giving HCl and aluminum trichloride as byproducts. This works well for secondary halides and simple primary halides. In a regular primary halide here, we can think of the electrophilic agent as this complex because we're not going to form a primary carbocation. But one of the problems with primary alkyl halides used in this reaction is that they have the tendency to rearrange. So remember, anytime we have a carbocation, and we can think of this complex here as acting like a carbocation on this position. That's how it reacts. Anytime we have a primary carbocation, if it can rearrange, it will rearrange. And in this case, a simple hydride shift will generate a secondary carbocation. So this is one of the limiting factors of this reaction, and we will address an approach to navigate through this limitation in the near future. So we're going to get a combination of products for this reaction. Minor product, substitution at the primary position. Major product, substitution at the secondary position. There are a few other limitations of the Friedel-Crafts alkylation reaction. First, the halide leaving group must be attached to an sp3 hybridized carbon. So in this case, with a sp2, aryl, or arene, no reaction will occur in either of these reactions. Often we'll obtain polyalkylation. Multiple positions can be alkylated. And if the aromatic ring has been deactivated with an electron withdrawing group, right? So the benzene ring is acting as the nucleophile. So the more electron density in the benzene ring, the more nucleophilic the benzene ring will be. If there's an electron withdrawing group, such as a nitro or an acyl group, that electron density is pulled out of the ring, and that reduces the nucleophilicity of the benzene ring. Another reaction that is quite similar to the Friedel-Crafts alkylation is the Friedel-Crafts acylation. In this reaction, we're also going to form a new carbon-carbon bond, but in this case it'll be with a carbonyl group. This reaction also helps us to avoid some of the limitations that were present in the Friedel-Crafts alkylation. This reaction will also be catalyzed by aluminum trichloride. So let's take a look at the mechanism. To begin with, chlorine from the acyl chloride, starting material, is going to attack the aluminum trichloride, and then this carbon-chlorine bond will break, which yields the acylium ion. If we look at the resonance structure of the acylium ion, it's resonance stabilized, which will prevent rearrangement, and also provides us with an extremely electrophilic carbon. This carbon has a positive charge in this position and will be readily attacked by the nucleophilic benzene ring. First step, nucleophilic attack, sigma complex formed, and then finally proton transfer reforms aromaticity. This reaction provides us with a direct route to a primary alkyl substituted benzene ring. To begin with, we can execute our Friedel-Crafts acylation, forming this ketone intermediate, and we won't get any rearrangements in this case. We'll just get this as the major product and only product. And then a Clemensin reduction, or zinc mercury, in the presence of acid and heat, will reduce the ketone down to the alkyl. So this provides us with an opportunity to synthesize substituted alkyl benzene rings. Another limitation of the alkylation reaction that we can avoid using the acylation reaction is the overacylation problem. Remember before, just a few minutes ago, we talked about an electron withdrawing group pulls electron density out of the benzene ring, which makes it less nucleophilic. So in this case, we're using that property to our advantage. After the first acylation occurs, a second acylation will not occur because we have deactivated the benzene ring. In the Friedel-Crafts Acelation, we will be forming a new carbon-carbon bond, but in this case with the carbonyl group. This reaction is also going to be catalyzed by aluminum trichloride. So we take an acyl chloride and react it with aluminum trichloride, and we can look at the mechanism of that. So first the chlorine attacks the aluminum, creates this intermediate, which then breaks the carbon-chlorine bond and forms the acylium ion. The acylium ion is resonance stabilized, so it will not rearrange, and it gives us a very electrophilic carbon. We then can undergo the standard Friedel-Crafts acylation mechanism. Now, if you remember before, we discussed how alkylation with a primary alkyl halide was quite difficult because it had the ability to rearrange. One way that we can avoid that, a way that we can create primary substituted carbon-carbon bonds with a benzene ring, is to begin by using a Friedel-Crafts acylation. Once we have our ketone intermediate, we can then reduce with zinc or mercury in acid and heat to obtain the carbon-carbon bond alkyl product. And this reduction is called the Clemensin reduction. Now remember, just a few minutes ago I discussed how if you add an electron withdrawing group to the benzene ring, we're going to reduce the amount of electron density in the benzene ring and make it less nucleophilic. So this also solves the problem of polyacylation or alkylation because we've provided an electron withdrawing group that makes the benzene ring less nucleophilic. So a second iteration of this reaction will not occur.